Chapter 8, Instantaneous and Timed Overcurrent Protection. The next step up from protection by fuses and involving relays is a common one. It is the instantaneous and timed overcurrent protection. Primarily is used in feeder protection because of long feeder lines. They lend themselves very easily to be coordinated by inverse time overcurrent or instantaneous protection. The overcurrent relay is the simplest type of protection relay. As its name implies, the relay is designed to operate when more than a predetermined amount of current flows into a particular portion of the power system. There are two basic forms of overcurrent relays. There is the instantaneous overcurrent relay, and there is the time delay overcurrent relay. Now, these two relays you see here, or this one relay actually, is old school type relays, but there's still a lot of them in service today, and a lot of them are being serviced. As you can see, both instantaneous and definite time relays are sometimes packed in the same case. And that is indeed especially true if you're using the modern IED relay, and the term IED refers to intelligent electrical device. It's not to be confused with the IED bombs that you find in war today. The IED in terms of relays refer to intelligent electrical device. And actually what the IEDs are basically computers that also have measuring devices in them. So they're very flexible. You can create many types of characteristics that you want to watch for in a line, the least of which are instantaneous overcurrent and timed overcurrent type characteristics. And we'll talk more about those later. The instantaneous overcurrent relay is designed to operate with no intentional time delay when the current exceeds the relay settings. Nonetheless, the operating time of this type of relay can vary significantly. It may be as low as 0.016 seconds or as high as 0.1 seconds. The time overcurrent relay, which is characterized by General Electric's IAC, IFC, SFC, or Westinghouse's CO relay, has operating characteristics such that its operating time varies inversely as the current flowing into the relay. The three most common types of timed overcurrent characteristics are listed here: is the inverse, the very inverse, and the extremely inverse. These curves differ by the rate at which the relay operates. Time decreases as the current increases. Electromagnetic overcurrent relays are based on electrodynamic forces produced on a moving part by the current flowing through the coil. Instantaneous relays operate without any intentional time delay. They are used for faults close into the source where the fault currents are very high. The construction of an instantaneous overcurrent relay is usually a moving armature and or a plunger, which operates when the current flowing through it reaches a certain point. You can adjust that point by a pickup screw in the armature, and definitely this is old school, but it demonstrates how an instantaneous overcurrent relay would operate. The equivalent electronic version of this would be the current is flowing into an electronic device, which would be a black box, which you can preset it at a certain point, and it triggers a flow of DC current to close a couple of contacts, which would essentially be doing the same thing. The inverse time response can be provided by an induction disk unit. In the induction disk unit, a metal disk is mounted on a shaft that can freely rotate. The current coils are fixed and create a magnetic field that induces eddy currents into the metal disk. The magnetic field of the eddy currents interact with the magnetic field of the stationary coils and produce torque on the disk. The disk and its shaft rotate and bring a moving contact towards the fixed contact into a closed position. The motion of the shaft is opposed by a spring that returns the disk and the moving contact to the open position when the current drops below a preset value. The time to close the contacts depend on the contact travel distance, which is set by a time dial, and the pickup current is adjusted by selecting current taps on a current coil. The relays are normally available, as we saw, with three ranges: broad ranges, inverse, very inverse, and extremely inverse, with current taps at 0.5 to 2.0 amps, 1.5 to 6.0 amps, and 4 to 16 amps. Now we are talking about secondary amps here that comes outside of a current transformer which is connected to the line. The time dial has usually positions marked from 0 to 10, where 0 setting the contact is permanently closed and 10 is the largest distance to which it has to travel. What you are about to see is an inverse time relay in action. It's going to be in the next slide. What you are about to see here is a GE IAC relay in action. We have it, or I have it connected up to a test set that is inducing a current into, or injecting a current into the relay above its preset level for timed overcurrent setting. So you will see the disk start to rotate in a clockwise direction as you're looking down on the top of it, and then you'll see the movable contact just below the numbered dial, straight above the disk, starting to move to the left. It will then make contact with the stationary contact, and that would essentially trip the breaker if it was connected up to this relay. It's hard to see the stationary contacts, and it's hard to see how things are operating, but you do get a sense of how the time works on these inverse curve type relays. So the test set was configured such that once contact was made, the current flowing into the current coil was disconnected and the relay was allowed to reset. This diagram shows the application of a couple of timed overcurrent relays on a radial feeder that flows from station A through station B. Superimposed over the diagram is a time curve showing the time characteristics of the overcurrent relays at the various stations. What it does indicate is that as you move down the feeder, if there is a short down the feeder, the time taken to operate the relays, because the current would be decreasing as the fault occurs further down the line, the time to operate the relay, because it's an inverse time relay, will also take longer. So that a fault, say just before station B, the time for relay at station A to operate is indicated on the diagram. We can set the inverse time relays on station B relays such that they would pick up prior to station A picking up, so that if a fault on the feeder further down past station B, the relays are coordinated with an inverse curve such that the relay B, or relay inverse time relay at station B, would operate before the relay at station A. But there is a backup feature to this as well, and that is if for some reason the relays at station B fail to operate for one reason or another, then we still are protecting the line, although it'll take longer to operate. The breakers or the relays at station A will still sense a fault down past station B, but it does give station B time to operate. If station B doesn't operate, then the relays will trip the breakers at station A and isolate the fault. Something else that relay designing has to take into consideration on such simple feeder setups is that after such a feeder has been out of service for a long period of time, especially in the winter when things are cold, and the off period of all intermittent loads is a long time, such as furnaces, refrigerators, pumps, water heaters, etc. Then when the breaker is closed to re-energize that line, these feeder loads are all calling for energy all at once, and the normal diversity that the feeder would experience as things come and go in proportional times isn't experienced. In other words, we have a total inrush current, also referred to as cold load pickup, may be approximately 4 times the normal peak load current. This inrush current decays very slowly and will be approximately 1.5 times the normal peak current after as much as 3 or 4 seconds. So in these cases, it might be wise to choose a more inverse or extremely inverse characteristic type relay that provides selectivity between the inrush and the short circuit currents. A minimum of 3 overcurrent relays and a total of 3 current transformers are required to detect all possible faults in a 3-phase AC system. 2 of these relays are usually connected in the phase circuits, and the third relay is usually connected in the residual circuit of the current transformer as shown here. Sensitive ground fault protection and protection against simultaneous grounds and different parts of the system is provided by this arrangement, whether the system is grounded or ungrounded. On 3-phase 4-wire systems, which represent a large percentage of the new installation, it is not always possible to balance perfectly the single-phase loads among the 3 phases. The use of sensitive residual ground overcurrent relays may not be feasible if the relay picks up under normal load conditions. For such systems, the 3 overcurrent relays are often connected in the phase circuits of the current transformers, and the sensitive ground fault protection is sacrificed. This is the GE inverse timed overcurrent relay. The adjustable setting variables are the tap setting, which is a screw adjustment along the top of the relay here. The time dial setting is here. It's a continuous setting. This shows a family of inverse time curves for the relay. A curve is shown for each numerical setting on the time dial scale. Any intermediate curves can be obtained by interpolation since the adjustment of the dial is continuous. Notice that the curves shown are plotted in terms of multiples of the pickup value so that the same curve can be used for any value of pickup. And the instantaneous pickup is achieved by a screw adjustment on the top of the coil solenoid. This is a Westinghouse or ABB type CO overcurrent relay, and it's almost identical in settings to the GE version, with the tap settings that adjusts the minimum pickup of the disc here. The time dial adjustment is shown here, and the curves are shown here. Again, there's a family of curves for this relay. A curve is shown for each numerical setting of the time dial, and intermediate values can be obtained by interpolation because the dial is a continuous, it's not stepped. Notice that the curves are shown here again, plotted in terms of multiples of the pickup value, so that the same curve can be used for any value of the pickup. And the instantaneous pickup is achieved by a screw adjustment. This diagram shows how the overcurrent relay, in this case the Westinghouse ABB CO type relay, is connected to monitor all three phases of a feeder circuit. Just out of interest, the designation of a CO relay describes the characteristic that you can expect with using that relay. For instance, a CO-2 is a short time relay, CO5 is a long time relay, right up to a CO11, which is an extremely inverse time relay. The connections to the system are the same, it's just that the characteristics and the time delays and curves will be different. Now, these overcurrent relays are good for radial feeders where the power flow, including the fault current, always flow in one direction. The problem arises when the evolution of a power system starts to tie feeders together, and then there is a possibility that power could flow in the opposite direction in order to feed a fault. And in this case, the overcurrent relays don't have any directional characteristic, so you're bound to get erroneous tripping or erroneous operations. So, how do we solve this problem? Well, we solve it using a directional type overcurrent relay. The overcurrent protection can be given a directional feature by adding a directional element. Directional overcurrent protection responds to overcurrents for a particular direction of power flow. If power flow is in the opposite direction, the directional overcurrent protection remains inoperative, or at least the operating torque is greatly diminished. The General Electric 12 IBC 53 relay comprises an overcurrent relay and a power directional relay in a single relay case. The power directional relay does not measure the power, but it is arranged to respond to the direction of the power flow. In looking at the internal workings of this relay, it helps to separate out the AC components from the DC components. The IBC relay is much the same as the previously studied overcurrent relay. However, the directional unit influences the timed overcurrent unit. The directional unit is made up of an induction cup unit that will rotate only for power flow in the direction of the feeder or the line and completes the circuit. Now, in order to measure directional or power directional flow, you need a voltage input as well to be compared to the current flow, and you have to feed in a phase to neutral voltage for that particular phase of the line. So the unit will measure phase to neutral voltage as well as the phase current, and then determine if power flow is going in the right direction. This relay uses old school trickery, which I won't go into right now, controlling the enhancement or the restraint of the operating coil of the timed overcurrent unit by switching it in and out or by switching in and out shaded poles acting on electromagnets of the disk movement. Because of the directional element, we need one relay for each phase that we are protecting in the feeder or the line. Notice that the PTs are connected phase to phase, but the relay coils are connected in star, creating their own neutral, providing the directional unit phase to neutral voltage that are required to measure the direction of the current flow. Now, in this day and age, with the introduction of computer-assisted or solid-state IED type relays that are out there that do a heck of a lot more and do it a lot more efficiently than these relays, it may seem superfluous to be going over some of this old school stuff. However, by and large, there's still a lot of these relays in service, and it helps to know the theory behind them and how they do work. In actual fact, you'll probably find in existing utilities a lot more of these relays than the new modern ones, although that is slowly changing as time moves on. The other thing to note is that these relays kind of demonstrate the theory very well, whereas the solid state ones are doing the same thing, but essentially they look like black boxes that are just connected to the system, even though they do the measurement and functioning a lot more efficiently. However, it helps to know this, and these are some of the relays you'll find when you're out there. Of course, the newer IED, intelligent electronic devices, such as this SEL 351 distribution and transmission relay, get rid of the need for old school trickery by using solid state magic. The SEL 351 protection relay is a microprocessor based distribution feeder protection management system. They call it a management system because it does a whole lot more things than just look after the overcurrent and directional overcurrent protection for the line. This protection IED is capable of managing a complete low voltage feeder protection system, complete with single or multiple shot automatic reclosing. As with most protection IEDs, the relay is also capable of logging sequence of events, fault oscillograph records, online metering, and distance to fault location measurement. So it does a lot more than the old school relays, and they are just getting better and improving more. But I thought we'd just have a peek at one of them just so that you would know what else is out there. This one happens to be manufactured and sold by SEL. There's other ones out there. This is just an example of one. Okay, at the risk of sounding like a sales pitch, which this is in no way intended to be, I thought I would just go over some of the features of this particular relay, and there are several other equivalent manufactured relays out there, but this one certainly is somewhat leading the pack, and I just wanted to point out some of the features that these new modern relays will do, while at the same time being able to provide the same logic of directional overcurrent protection that the old school relays used to be able to do. This particular relay has voltage and load encroachment control for 4-phase time overcurrent elements for load security. It has 6 levels of phase, negative sequence, neutral, and residual overcurrent elements. It has communication tripping scheme logic for rapid clearing of faults. It has a programmable 4-shot recloser with synchronism for synchrocheck reclosing. It has phase and sequence under and over voltage elements for increased control scheme flexibility. It has 6 steps of accurate frequency elements for multi-level under and over frequency trip control. It has event recorders. It records events and stores them and will release them on interrogation. It does breaker monitoring, which uses the breakers manufacturer's published data for maintenance scheduling. It has substation battery monitoring. It has flexible logic for traditional panel switches and latches and indicating lights. It also has EIA 232 and EIA 485 serial ports for local and remote access. Now, modern relays tend to talk to each other, and that's what these communication ports will do, and it gives you a whole lot more flexibility for protecting your station and your feeder lines. It also has an accurate fault locating system for quick circuit restoration and increase of serviceability. In other words, it will point out where the fault is so that the line crew could get to it more quickly and do the repairs. It also has a complete high accuracy metering elements for not requiring the use of external meters. Now, these aren't necessarily used for billing purposes, but certainly for control and for monitoring for the actual supplier. It gives you the accurate metering that's required. This relay is also extremely flexible, and then you have a choice of amperages that you can feed into it. You can have 5 amps or 1 amp for the phase current inputs, or 5 amp, 1 amp, or 0.05 amp for the neutral current input. So these relays are extremely flexible, and primarily because they're like a small computer, but they do still look after the old logic of directional overcurrent type relays. And having said all of that, this essentially is what the relay looks like in its logic circuit and one-line diagram when it's plugged into the system. You can see that it does a whole lot more than just overcurrent protection. Let's look briefly at distribution and low voltage feeder protection. Electrical distribution is the final stage in the delivery of electricity to the end user. The distribution system's network carries electricity from the transmission system and delivers it to the customers. Since the transmission system is typically rated from about 130 kV up to, could be as high as 700 kV, substation step-down transformers are used to bring the voltage levels down to under 50 kV levels for distribution to the customers. As the distribution system is rated up to 50 kV, many large industrial end users will be fed at these voltage levels and will supply their own on-site substations that will step down the voltage to more useful voltage levels for the facility. For consumer consumption, various step-down transformers and pole-mounted transformers will be located in the geographical region that will supply the electricity to the customer. Distribution networks are typically of 2 types, radial or networked. A radial feeder leaves the station and passes through the service area with no normal connections to any other supply. This is typical of long rural lines with isolated load areas. A network system having multiple connections to other points of supply is generally found in more urban areas. These points of connections allow various configurations by the operating utility by closing and opening of switches along the feeders. Operation of these switches may be by remote control from a control center or by a lineman or crew sent out to do the switching. The benefit of the network model is that in the event of a fault or required maintenance, a small area of network can be isolated and the remainder can be kept in service. With these networks, there may be a mix of overhead lines utilizing traditional utility poles and wires, and increasingly underground construction with cables and indoor or cabinet substations. Underground distributions, however, are very or significantly more expensive than overhead construction, and therefore often co-located with other utility lines in what is called common utility ducts. This is a representation of a typical distribution station. It has basically the minimal amount of equipment required. Lines, high voltage lines coming in, you can see them at the left, coming into a system of potential or voltage transformers for measurement of the voltage coming in, passing through a step-down transformer to a distribution bus and circuit breakers, and then going out on the line, as you can see over to the right-hand side. There is usually a control house associated with a distribution station that houses the relays and the metering and the communication gear that's required to run the station, and the station can be double this size if it has two transformers and two sets of lines coming in, and very seldom do you only get one set of feeders coming out of a distribution station. You usually have a low voltage bus that facilitates anywhere from 4 to 10 feeders coming out of the station, and certainly the protection schemes would have to be multiplied by the numbers of equipment that are in the system. Faults occurring on overhead and underground distribution feeders are caused by various sources, including faulty equipment that could cause trips. Environmentally, of course, we would have wind, lightning, ice, snowstorms, sag due to extreme temperatures, and even salt spray from the roads could build up and cause faults. You can also have falling tree limbs. You could have animals that are getting up into the system, and also people can cause outages and faults along the line as far as poles coming in contact with the pole line feeders, either hitting them with cars, or could be people even just throwing stuff over there, or even in the case of new construction or somebody doing underground digging, they could come in contact with the feeder circuits that are in an underground system. All of which we try to avoid as much as possible, but these are the things that do cause system faults and outages. Faults occurring in the distribution system must be sensed quickly and immediately, and isolated to prevent hazards to the general public and the utility personnel. Protective relays are used to sense short circuit conditions caused by faults in distribution protection schemes, and the use of proper schemes and settings can help to maximize sensitivity and selectivity. Basic feeder protection principles are well known. Phase and ground overcurrent usually function reliably to detect most faults. Reclosing is often applied to restore service following temporary faults on overhead circuits. The challenge in feeder protection is reliable operation during unusual fault events such as high impedance ground faults and adjacent feeder faults. A key advantage of microprocessor-based feeder relays is the ability to protect against these unusual faults while improving the operation of the distribution system through flexibility, programmability, and communications. In radial feeders, the power flow is one direction only, that is from the source to the load. This type of feeder can easily be protected by either definite time relays or inverse time relays. Line protection by definite time relays is very simple. Here, the total line is divided into different sections, and each section is provided with a definite time relay. The relay nearest to the end of the line has a minimum time setting, while the time setting of the other relays successfully increase towards the source. For example, at point D, the circuit breaker CB3 is installed with definite time relays of 0.5 seconds. Successfully at point C, another circuit breaker CB2 is installed along with definite time relay operating with a time delay of 1 second. The next circuit breaker CB1 is installed at point B, which is nearest the point A, and at point B the relay is set for a time of 1.5 seconds. Now assume a fault occurs at point F. Due to this fault, the faulty current flows through all the current transformers or CTs connected in the line. But as the time of operation of the relay at point D is a minimum, the CB3 associated with this relay will trip first to isolate the faulty zone. And if due to any reason CB3 fails to trip, then the next higher time relay will operate to associate the CB to the trip. In this case, CB2 will trip. If CB2 also fails to trip, then the next circuit breaker will trip, and CB-1 will trip to isolate the major portion of the line. There are, of course, advantages and disadvantages to this type of line protection. The main advantage is, of course, its simplicity. The second major advantage is during faults, only the nearest circuit breaker to the fault, and that's the farthest from the source, will operate to isolate the specific position of the line that has the fault, resulting in the fewest number of customers being interrupted. The disadvantages to this system is that if there are a number of different time zones that have to be introduced, the time setting of the relay nearest the source would have to be very long. And this could approach the time where things start to break down in the system. So the more positions that you have to set times for, the less effective that this protection will be. The drawbacks, as we just discussed in definite time overcurrent protection of feeders, can easily be overcome by the use of inverse time relays. With inverse relays, the time of operation is inversely proportional to the fault current. The overall time setting of the relay at point D is at a minimum, and successfully this time setting is increased for the relays associated with the points towards point A. Any fault at point F will obviously trip CB3 at point D. In failure to operate CB3, CB2 will still operate, but at a later time than the relay would have operated at point D. Although the time setting of the relay nearest the source is going to be higher, it will still trip in a shorter period of time if a major fault occurs near the source, as the time of operation of the relay is inversely proportional to the faulty current. In other words, a fault closer to the source is going to draw a heavier current, so it's going to cause an inverse time relay to operate at the bottom of the curve, which would be much faster than which would be further up the curve, which would be the setting further down the line. Sometimes, for maintaining the stability of a system, it is required to feed a load from the source by two or more feeders in parallel. If a fault occurs in any of the feeders, only that faulty feeder should be isolated from the system in order to maintain the continuity of supply from the source to the load. This requirement makes the protection of parallel feeders a little bit more complex than the simple non-directional overcurrent protection of the line, as in the case of the radial feeders. The protection of parallel feeders requires the use of directional relays and the grading of the time setting relays for selective tripping. Okay, let's look at the case of these two feeders connected in parallel. Both of these feeders will have non-directional overcurrent relays at the source end. These relays should be the inverse time relay type. Both of the feeders have directional relays or reverse power relays at their load end. The reverse power relays used here should be of the instantaneous type. That means these relays should be opened as soon as the flow of power in the feeder is reversed from the normal direction of power flow from the source to the load. Now, suppose a fault occurs at point F. Say the fault current is IF. This fault will get two parallel paths from the source, one through circuit breaker A only, and the other via circuit breaker CB-B, feeder 2, CB-Q, load bus, and CB-P. This is clearly shown where IA and IB are currents of the fault shared by feeder 1 and feeder 2 respectively. IA plus IB is equal to the fault current IF. Now, IA is flowing through CBA and IB is flowing through CBP. As the direction of flow of CBP is reversed, it will trip instantaneously, but CBQ will not trip, as flow of current or power in this circuit breaker is not reversed. As soon as CBP is tripped, the fault current IA stops flowing through the feeder, and hence there's no question of further operating of inverse time overcurrent relays on feeder 2. IB still continues to flow even though CBP is tripped. Then, because of overcurrent IB, CBA will trip. In this way, the faulty feeder is isolated from the system. This ends Chapter 8.